Hello all. In this video, we'll be discussing portfolio optimization. Now, there are many ways one could optimize a portfolio, and in this video, we'll be discussing how do you optimize your portfolio by maximizing the Sharpe ratio. So, we'll be going over this concept called the modern portfolio theory or MPT, which basically optimizes returns for a given level of risk that you want. Okay, so let's start with the basics. So, let's start with the first thing, which is returns. The returns is we'll define the log returns, right? And the log returns is just simply the log of future price over today's price. And the expected return is just taking the mean of your daily returns of an asset. So if you have 200 assets with you, your expected return is basically just the mean of the daily returns of each asset. So your vector that you have will have 200 elements, and obviously your portfolio is a vector of weights, right? Which basically represent how much capital you have distributed amongst your assets. So your expected return of the portfolio will just be the dot product of your weights vector and your expected returns vector, which is basically the summation of alpha I wi. And the second basic term is risk. So every asset has a risk, or every asset has its variance, right? And this is because, see, we are talking about returns of an asset, and this returns is just a random variable. So it will have, I mean, every asset will have its own variance. And if we consider a portfolio to have only two assets, which is not usually the case, the variance of this portfolio will be the variance of R1, which is the variance of returns of variance of returns of asset 1 plus variance of R2 plus 2 times covariance of R1 and R2, right? And if we have, in the general case, a portfolio of M assets, we first need to define the covariance matrix to find the variance of this portfolio. The covariance matrix is defined like this, which the elements of the matrix is sigma I comma j, and if I and j are both the same, then that would represent the variance of the returns of that asset. And if I and j are not same, that would mean the covariance between the returns of assets I and j. And this variance of the portfolio can be found to be W transpose times sigma times W. The W transpose is because, see, our W is an M times 1 vector, right? And when you do W transpose sigma W, you get 1 times M times M times M times M times 1, which will give you a scalar, right? So that would be your that would be your portfolio's variance. And to find the standard deviation, you have to just take the root of it, right? And so let's begin to code for finding the portfolio's returns and risk, right? So let me just make a new notebook here. Let's call it YouTube portfolio optimization. Yeah, so let's begin. Def portfolio return, right, which would take in inputs, weights, and returns. The logic is simple: return np dot sum of returns dot mean and multiplied by weights, right? And we're multiplying by a factor of 252 because we want to analyze our portfolio return. Similarly, we will define our portfolio risk function, which takes in the same inputs, and it would return the square root of the dot product of the transpose of weights and the dot product of weights and dot product of returns and weights. Oh, I forgot to mention one thing. We have not found out your matrix, right? Your covariance matrix. So let us find that out first. So returns cov is equals to returns dot cov times 252, right? And let us put that here. And yeah, these two are the functions for portfolio returns and portfolio risk, right? So let us try to analyze this whole, portfolio optimization thing and your MPT by just taking a portfolio with only two stocks. Okay, let's have two stocks of Amazon and Microsoft. Right. So first, I just import some packages, essential packages. So NumPy, Pandas, Finance, Yahoo Finance, and Matplotlib dot pyplot is PLT. Right. And let us download Apple's and Microsoft's price. So not Apple, Amazon. Let's take Amazon. MSFT. Right. Let's start from all the way back 2010 0101, and let's set auto adjust to be false, and then call your adjusted close price. And now we need to define your returns column, right? So returns will basically just be np.log prices over prices dot shift, right? Yeah, let's execute it. Okay, so we have created our returns vector or your returns column for both Amazon and Microsoft. And now we want to figure out, okay, so this is what we are going to do. We are going to basically plot a graph for the returns versus risk for different portfolios, right? So you'll have different portfolios. You can have thousands and 2,000s of different portfolios. By that, basically what I mean is you can have different distributions of weights across your two assets, Amazon and Microsoft. You can put 100% of your capital into Amazon and 0% Microsoft, or you could put 100% in a Microsoft and 0% Amazon, right? So let us, uh, let us create a weights array for Amazon, which is from 0 to 1, right? So Amazon weights is equals to np dot lean space 0 comma 1 comma 100, right? And let us just define a portfolios array which will basically contain the return, the portfolio return comma risk of your 100 portfolios, right? So we'll be looping over every weight in Amazon weights, right? So for W1, let's call it W1 in Amazon weights, you'll get your W2 to be 1 minus W1, right? And you will find out your portfolio return by calling this function right over here. Okay, so we have to define your weights to be right, and you have your returns here. Cool. Your p risk to be the same thing, except here it should be a risk, right? And then finally we'll put this into our portfolios array. P risk comma p return. So I am putting p risk as our first element because I want p risk to be on my x-axis and p return to be on my y-axis, right? And I convert this portfolios array to a numpy array. Portfolios numpy dot array portfolios, right? There seems to be an error. List has no attribute t. What? Okay, my bad. So I'm converting this to an numpy array, right? So yeah, should work. NumPy is not defined. My bad. My bad. Where did I do this? Right. Okay. So now that's sorted. Now let us plot returns versus risk for all the portfolios that we have here. So PLT dot figure fig size is equals to 12 comma 7, and then PLT dot plot portfolios, all of them, right? And let us plot it in red color. Let's label the x-axis to be, what is our x-axis? Our portfolio risk, and your y-axis is portfolio return, and let us plot it. So as you can see, you get this graph here. It is a curve, and you see for a particular risk here, let's say 0.25, you get two different portfolio returns, and obviously you want the higher one. And so this graph can be divided into two parts. You can basically take, the portfolio which has the lowest risk as a divider and divide this curve into an efficient portfolio frontier and an inefficient portfolio frontier. So I've pasted these two cells. Basically, the first cell figures out what portfolio is our minimum risk portfolio and gets its risk and return. And then we use it as a mask to find all the portfolios which has the return higher than this minimum risk portfolio return, right? And we get our two, divisions, which is efficient portfolios and inefficient portfolios, right? And then we just plot it, and it would be something like this, as we have discussed before. And what else? So, as I've mentioned before, this is called the efficient frontier, and this is called the inefficient frontier. This purple dot basically is the 100% Amazon point, wherein you put in 100% of your capital into Amazon, and this green point basically means you're putting in 100% of your capital to Microsoft, right? And now we need to figure out which point on this, curve has the highest Sharpe ratio. So let us do that. So let us have max Sharpe is equals to 0, and let us define this vector, which is most efficient portfolio vector, which is basically an array of your risk comma return, right? And we are basically going to, go over all the portfolios that we have here and calculate a Sharpe ratio, and then figure out what which portfolio has the higher Sharpe ratio. And now to just quickly, brief over the definition of Sharpe ratio, I have defined it here. I'll just quickly discuss over two things: risk-free assets and Sharpe ratio. So, risk-free assets is nothing. It basically means, as the name suggests, basically means that you get some return from zero risk, and any investment that investors hold should have a higher return from the return that you get from this risk-free assets. And Sharpe ratio is basically the extra return that you get from every risk that you take, right? So it's defined as RP minus RF over the risk of the portfolio. RP is just the return of the portfolio. RF is the return that you get from your risk-free assets. And the higher your Sharpe ratio is, the better your portfolio is. The better it's able to convert the risk into excess returns. And so we want to maximize this, uh, equation over here and find the optimal portfolio. So coming back to finding out the portfolio with the highest Sharpe ratio. So we'll loop over all the portfolios that you have in your portfolio array. So for risk comma return in portfolios, right? That's how we defined our portfolios array, right? So we we first have to define your Sharpe ratio function, right? How do we calculate the Sharpe ratio? So let us first define your Sharpe ratio function, which takes in your portfolio return, your portfolio risk, and your risk-free return, which I'll define here to be 0.02, and it will return P ret minus RF over P risk, right? And now we will quickly find out the Sharpe ratio for this particular portfolio that we have taken. I mean, ret, comma, risk, comma, 0.02, right? And if this SR is greater than the max Sharpe, then I will set my max Sharpe to be SR and put in this risk, comma, return on our most efficient portfolio. Risk, comma, ret. That makes sense. Let's execute both the cells and now let us plot the whole graph. Right. So I'll just use the code that I have in the other Jupyter notebook. So there we go. I have not, yeah, right. So I have used another variable name in that notebook. So here it is most efficient portfolio. And we are using the risk-free return to be 0.02 here as well. And I'll explain all these things, tangency portfolio and capital market line in a few seconds. And nothing else, right? Yeah. So yeah, you would get this graph. So what have we done here? We have basically just plotted your efficient frontier, right? And we have joined the line between your risk-free return point and the max efficient portfolio point on this efficient frontier, right? So this line that connects both the points is called the capital market line, right? And try to understand this, right? So this line here has the highest slope because as it just goes by the definition of Sharpe ratio, which is RP minus RF over the risk of the portfolio, right? So for any other point on this graph, the line joining that point, for any other point on this curve here on the sufficient frontier, the line joining that point to this risk-free return point would be having a slope lesser than this capital market line given here, which follows the definition of Sharpe ratio. Right, and this portfolio here, which has the highest Sharpe ratio, is called the tangency portfolio. And since this slope here is the highest, it will be tangential to this curve here, if that makes sense. Having understood all these basic terms and having analyzed, how the graph would look like or how we are trying to optimize our portfolio for two stocks, namely Amazon and Microsoft, I think we are good to go for a whole universe of 500 stocks. Let's take the S&P 500 stocks. So I have the code ready with me for that as well, for just, downloading the data from this Wikipedia page, which has all the tickers of the S&P 500 stocks. So there we go. So we have gotten our S&P 500 tickers. And now let's download it from Yahoo Finance, the data. So prices is equals to yf dot download tickers start is equals to let's let's not go very back. Let's take it only from 2020. Start is that much. Then let's set auto adjust to be false. And let's take in the adjusted close, right? And let us first drop the NANs in this prices. And let us define our returns column np.log prices over prices dot shift dot drop in a, right? Okay, so since this is an optimization problem, we should necessarily pre-compute some things like mean returns and the covariance matrix to like save up execution time. So let's quickly get those. Mean returns is equals to returns dot mean, right? And your cov returns will be returns dot cov, and we'll multiply by 252 because we are analyzing it, right? And then we'll define our functions, right, for portfolio return and portfolio risk. So this function will take in the weights, the mean returns, and return np dot dot weights and mean returns, right? And times 252 because of analyzation. Then p risk, weights, mean, curve returns, right? And then return np dot square root np dot dot weights dot transpose np dot dot curve returns weights, right? You have these two functions. Let us, okay, so now since we are dealing with an optimization problem and this problem deals with finding the maximum Sharpe ratio, right? We are trying to find out the portfolio for the which has a maximum Sharpe ratio to be our optimal portfolio, right? So what we'll be doing here is we'll be using the minimize function from scipy.optimize, right? And because of that, we'll define the negative of Sharpe ratio. We'll define a function which computes the negative of Sharpe ratio, and essentially the minimum negative of the Sharpe ratio that we get will be the maximum positive Sharpe ratio that we have, and we'll select that portfolio as our optimal portfolio, right? So define, or let's define our function. Define negative Sharpe, which takes in weights, takes in the mean returns, takes in the covariance matrix, and let's set RF to be 0.02, right? And let us quickly compute RP return to be this thing over here, portfolio return, portfolio risk is equals to P risk weights comma cov returns, and finally return the negative of our Sharpe, which is portfolio return minus RF over portfolio risk. So we need to define three more things, which are constraints, bounds, and initial weights. So let us set our constraints to be that the sum of weights across our assets to be 1, right? Because we want to basically allocate 100% of our capital into our assets, and we'll define our bounds to be that the weights for every asset that we have, or like the weight for every asset to be between 0 and 0.5. That basically means that we are not shorting any of our assets, and that we are not putting more than 50% of our capital into any asset, right? So this is the code for that. So constraints is equals to, the type is an equation, and the function is that the sum of the weights minus 1 should be equal to 0, and the bounds for every weight is that it should lie between 0 and 0.5. Right. And finally, we have to define our initial weights. So let us do that. Initial weights is equals to numpy dot array 1 over. Let us initially just uniformly distribute capital into every asset. So 1 over returns dot shape 1, right, times returns dot shape 1, right. Okay. And now let us write the optimization code. So first let's import minimize from scipy.optimize, and finally our optimized results, which is minimize the negative sharp. We have our initial weights with us. Our arguments are these things right over here. And not finally, yeah, so our method that we'll be using is something called the SLSQP, right? SLSQP. So this method tries to iteratively solve a nonlinear problem which has some equality and inequality constraints, which is what we are dealing with here, right? And we have some constraints with us and some bounds that we have defined earlier, right? And I think we are good to go now. Okay, that's running. I think it's fine. And we'll basically get our optimized weights in the x parameter of optimized results, right? And let's run that as well. Okay, the optimization is done. Now let us display the portfolio return that we get, the portfolio risk, and the Sharpe ratio, obviously. And one more thing, I'll tell what that one thing is after we compute these three things. So let us print our print. Okay, first let's compute our portfolio uh, or efficient portfolio return, which is P return. uh, we, we get our optimized weights. Let's rename this to be opt weights, right? So opt weights. Okay, so opt weights, and you have your mean returns with you, your efficient portfolio risk, P risk, you have your optimized weights and your covariance matrix with you, and finally we have our Sharpe ratio, right? So our Sharpe ratio would just be the negative of the negative Sharpe that we have defined, right? Optimized weights mean returns, or wait, we already have, okay, never mind, we'll just implement it, and 0.02. And now let's just print these things. So print uh, efficient portfolio return is FP return, right? And then print efficient portfolio risk and efficient portfolio Sharpe ratio, right? So risk is efficient portfolio risk, and finally efficient portfolio Sharpe ratio is the Sharpe ratio right over here. And let's see what we get. Okay, what happened? Oh, right. Okay. So we get a return of 0.34, which is very nice. And okay, the risk, I mean, since we have a very nice return, it is accompanied usually by a very high risk of 0.21, which we have here. So that would mean that whenever we like we have some kind of expectation, right, of how our portfolio would work, and we can, say that our return that we would get would be between 0.34 minus 0.21, to 0.34 plus 0.21, which would be from 0.13 to 0.55, right? That is what we can expect our return to be. And our Sharpe ratio is also quite good, which is 1.54. So yeah, I mean, this seems to be a pretty good portfolio. And one thing to, be careful here is that this minimize function that we have imported from scipher.optimize kind of is sensitive to your initial weights that you have set. And so it will be beneficial if you, loop over certain initial weights, certain initial random weights that you set for your assets to get, the portfolio with the highest Sharpe ratio. And yeah, one thing that we can see is how much of your, how many assets in your portfolio have the weight allocated to it more than some 0.1%, right? So we can do that by just executing this line of code here. So print number of stocks in portfolio, length of, so our variable is opt weights, right? And let's see how many stocks are there which have more than 0.1% allocation to it. So there are 16 stocks in our portfolio which have an allocation of more than 0.1. So this is the implementation for portfolio optimization by seeing which portfolio has the highest Sharpe ratio. And we have also covered a little bit of modern portfolio theory over here. I've also uploaded this original notebook of mine which covers everything that we have discussed in this video in great detail, and also some details on risk-free assets, Sharpe ratio, and the formula for capital market line, and some light discussion on the conclusion that we have gotten for our portfolio optimization on our S&P 500 universe. So feel free to check that out. I'm attaching the link in the description. Thank you.